The Hubble Space Telescope image of the interstellar object 3I/Atlas, obtained on July 21, 2025, represents one of the most intriguing astronomical observations in recent years. The image reveals a diffuse glow of light concentrated ahead of the object's direction of motion toward the Sun, a feature commonly interpreted as a coma formed by dust and gas released from the surface. Notably absent, however, is any sign of a classical cometary tail extending away from the Sun, which immediately sets 3I/Atlas apart from typical solar system comets. The glow appears asymmetric and compact, suggesting that it originates from localized processes on or near the nucleus rather than from a large-scale interaction with solar radiation pressure. This unusual morphology prompted a closer examination of the surface brightness profile and its physical implications. Figure 3 of the analysis paper shows that the surface brightness of the glow decreases extremely steeply with distance from the nucleus, following a projected power law slope of approximately -3. When translated into 3 dimensions, this corresponds to an emissivity profile that scales as the inverse fourth power of radial distance. Such a steep slope is not observed in ordinary comets within our solar system, where dust and gas outflows typically generate shallower profiles. In standard cometary physics, a steady-state outflow of material from a nucleus naturally produces a density profile that falls off as 1 over the square of the distance. When this material scatters sunlight, the resulting brightness profile reflects that same density distribution, leading to a much flatter radial decline than what is seen around 3I/Atlas. This discrepancy motivated the exploration of alternative physical models. In collaboration with Erikito, the realization emerged that a 3-dimensional emissivity slope of -4 can arise naturally if the dust outflow is illuminated not primarily by the Sun, but by a central light source embedded within the outflow itself. In this scenario, the density of dust still declines as 1 over r squared, as expected for a steady outflow, but the illumination intensity also decreases as 1 over r squared because the radiation originates from the nucleus. The combination of these 2 effects produces an emissivity proportional to 1 over r to the 4th power, precisely matching the observed profile. This model has the advantage of explaining the steep brightness gradient without requiring exotic dust dynamics or finely tuned evaporation processes. If the nucleus of 3I/Atlas is indeed generating its own light, the implications are profound. The observed brightness would no longer require a large reflecting surface to intercept and scatter sunlight. Instead, a much smaller object could appear comparably bright if it were luminous. Under the conventional reflection model, the inferred diameter of 3I/Atlas could be as large as 20 kilometers. Such a size is highly problematic from a statistical standpoint. Calculations of the interstellar population of rocky bodies indicate that objects of this scale should be extraordinarily rare. Given the limited reservoir of solid material in interstellar space and the vast volume over which it is distributed, the expected delivery rate of a 20-kilometer interstellar rock into the inner solar system would be on the order of once every 10,000 years or longer. The detection of such an object within just a few years of discovering the first 2 known interstellar visitors would strain credulity. The context in which these ideas crystallized is worth noting, as it underscores the human element of scientific discovery. Following the annual soccer cup match at Harvard's Institute for Theory and Computation, where the faculty narrowly lost to the students despite a strong performance, attention quickly returned to the cosmic puzzle posed by 3I/Atlas. Sometimes intellectual clarity emerges most sharply after emotional disappointment, and the morning after the match proved to be particularly productive. A key quantitative estimate emerged. The luminosity required to account for the observed brightness of 3I/Atlas, if it were self-luminous, would be on the order of 10 gigawatts. While enormous by human standards, this power output is modest on astronomical scales and could, in principle, be produced by a compact object through a variety of mechanisms. Another crucial insight followed from the steepness of the brightness profile itself. Regardless of whether the light originates from reflected sunlight or from intrinsic emission, the fact that the brightness declines so rapidly with distance implies that the nucleus dominates the observed light. The extended glow contributes comparatively little to the total flux. This conclusion is robust and largely model-independent. It means that any explanation must account for a bright central source, with the surrounding material acting only as a minor modifier rather than the primary emitter. When sunlight is considered as the dominant illumination source, serious difficulties arise. A rocky nucleus reflecting sunlight can only intercept a small fraction of the solar flux because of its limited surface area. The scattered light from such a surface would be overwhelmed by sunlight, scattered by dust distributed over the much larger region resolved by the Hubble image, which spans roughly 10,000 kilometers. In a steady outflow illuminated by the sun, both the dust density and the scattered light would follow a 1/r² dependence, yielding a brightness profile far shallower than the observed 1/r to the fourth power. There is no straightforward way to reconcile this mismatch within the framework of standard reflection. One alternative explanation invokes a halo of icy particles that scatter sunlight but rapidly evaporate as they move away from the warm, sun-facing side of the nucleus. This could potentially suppress the formation of a tail, since the particles would disappear before radiation pressure could push them into a trailing structure. For this model to work, however, the evaporation timescale would need to be extremely short, on the order of 10 minutes. Such rapid sublimation raises questions about the physical plausibility of the particles involved, including their composition, size distribution, and thermal properties. Moreover, it remains unclear whether this process would naturally produce the exact 1/r to the fourth power brightness profile seen in the data, rather than some other steep but less specific decline. By contrast, the centrally illuminated outflow model directly reproduces the observed profile, with minimal assumptions. It also alleviates the size problem by allowing the nucleus to be much smaller than 20 kilometers. A compact, luminous object embedded within its own dust cloud would appear bright while remaining consistent with the expected statistics of interstellar bodies. This possibility invites deeper reflection on the nature of 3I/Atlas itself. Interstellar objects are not obligated to resemble the comets and asteroids of our own solar system, which formed under very specific conditions. They may instead represent a far broader range of physical states, histories, and energy sources. Ultimately, the case of 3I/Atlas highlights how a single observational detail, a steep brightness profile, can cascade into a rethinking of fundamental assumptions. Whether the object is powered by an unfamiliar natural process or something even more exotic remains an open question. What is clear is that standard models struggle to accommodate all of the observed features simultaneously. As additional data are collected and theoretical work continues, 3I/Atlas may force a revision of how interstellar objects are interpreted and classified. For now, it stands as a reminder that the universe often presents phenomena that challenge expectations, inviting both skepticism and imagination in equal measure.